Un gusto presentar a Gabriel Raposo, que viene de UC Berkeley. Gabriel ya está terminando su doctorado en Berkeley con Marine Goring. Vamos a hablar de fluctuaciones de tableros de Young.
So thank you so much to the organizer for the invitation to give a talk. I'm very happy. Actually, it's essentially the first serious research talk I did in Chile, so it's great. So we'll start with some preliminary definitions just to make sure everyone's in the same page, and then we'll move on to next results. So first, what's an integer partition? So a partition is a collection of non-negative integers, so lambda 1, lambda 2, etc. We ask them to be decreasing, and we ask the sum of them to add up to n. We say that a partition of n is such a collection of integers. So integer partitions have a graphical representation that we call a Young diagram, which is the figure you have here on the left. So what we do is we simply draw boxes with the number of boxes in each row corresponding to the entry to the coordinates of the partition. And the standard Young tableau, the definition just below, it's a filling of a Young diagram with integers 1 up to n in such a way that no integer is repeated. I want them to be increasing from left to right and up to down. So during the rest of the talk, I want you to think that a standard Young tableau is just a dynamical version of a partition. What I mean here is that secretly in a standard Young tableau, we actually have a collection of partitions. We have a way of constructing a partition of size n. Starting from the empty partition, we just add boxes. And when a box corresponding to the number we have on the entry of the standard Young tableau. So you can see at each step, we always have partitions. So starting from a partition of size 0 up to a partition of size n. Okay, so these are going to be the main objects we're going to work during the rest of the talk. And we're going to talk about random partitions, random Young diagrams, and random standard Young tableau. Okay, so this is a probability seminar, so let's put some probability measures on it. So suppose that you have a probability distribution, rho n, on a partition of size n. So a question we can ask is what kind of behavior can we observe for a partition as n goes infinity? So, of course, the answer does depend on the distribution you choose. So let's start with the historical example, the Planck-Shell distribution. So the Planck-Shell distribution is defined as follows. It is defined to be the probability to see a partition of lambda size n is going to be dimension lambda squared, where dimension lambda is the number of standard Young tableau shape lambda divided by n factorial. So this means that there is a way to compute this, right? So if you want to know what the probability of seeing some specific partition, just draw the Young diagram, just fill with numbers, find all possible standard Young tableau, and then you compute this number, you have something. So if it is the first time you're seeing this distribution, then some questions may arise. So the first one is, well, even from the definition itself, it's not necessarily clear that this is a probability distribution. And secondly, okay, why this kind of very specific distribution and not something like, I don't know, uniform distribution, which is what we kind of think of as a first thought. So there's two reasons for that. So the first reason is that secretly, here we're actually working with a uniform distribution, only not on partitions, but on permutations. So there is a map, which is not important, I know, but it's called the Robinson-Shantes correspondence, which starts from a permutation and allows you to construct a partition from it. So if you take the push forward of the uniform distribution on permutations, then you obtain a distribution on partitions. The distribution is precisely the Planck-Shell measure. Okay, so that's one reason, but okay, why do we care about this particular map? So the reason is that it allows to study certain problems from permutations by studying this distribution over partitions. So it happens that the length of the longest increases to sequence on a permutation corresponds exactly to the length of the first row of a random Planck-Shell partition. So if you want to study some statistics associated to this number, for example, what is the limiting expectation as n goes to infinity or the fluctuations, so you can study partitions under the Planck-Shell method. Okay, so now we have an example of a distribution for partitions in mind, and we can try to answer this question. So what kind of behavior can we observe for this partition under this distribution? So something that happens is that when you draw these partitions, and here we're just taking the partition, using the Young diagram, and then rotating and reflecting. So we have this kind of function. And then choose n very large, and you sample some Planck-Shell partition, then you notice that the shape tends to concentrate around some limiting function. So this theorem was proved by Vershik, Rob, and Logenschep in 1977, and they actually found that if you think of this Young diagram as a function, then it converges in a certain way to some limiting function that has been found explicitly, which is the function.
Just to check, what the reason why you are reflecting is because of the dimension of lambda square?
No, the reflection is not really important. Actually, symmetric on a partial distribution, so it's not important at this stage. So the reason is not because of the reflection, but the reason we're studying this is because there is three classical ways of drawing partitions. So one is the English notation, which is the one I used at the beginning, but there is also French notation, which is a reflection. There's also Russian notation, which is this one. And Russian notation is kind of preferred because then you have a function, which is nice. So there is some space we can embed this thing and these kind of things.
So Vershik can get over Russian.
Yeah, I'm version of Russian math. So yeah, so that's a very important, I guess. So already for this result, we can already see some things. So you can notice that after studying the scaling, that the length of the first row will converge to square root of 2, up to square root of 5, which is something nice. So this is just for one distribution, but what can be said for other distributions? So for the Planchial distribution, which is the example they must study, first you have the result that is presented, so you have some limiting shape. But then we can ask about the fluctuations around this limiting shape. So this was studied by Ivan Obolshansky, which is also Russian, based on some previous work of Kerov. And very interestingly, when studying the local fluctuations, so local fluctuations mean the fluctuation of the first row, second row, third row of the partition. Then the fluctuations around these local statistics happen to be related to the Tracy-Widom distribution and Airy process. So these are exactly the same fluctuations you observe for any values of random matrices, for large families of random matrices. So this kind of observation is very nice because it means that we can put together in some sort of random partition, random matrix, another kind of object in the same framework. So we're not going to go deeper into that for now because we're going to focus during the rest of the talk about global fluctuations. Now, this is just about Planchial, but there is a lot of other distributions that have been studied, particularly in the last 20 years. So there is the Gelfand, Shurwell distribution, Ku-Planchial, Jack-Planchial, a bunch of deformation Planchial distribution. And this is only about random partitions still. But then if we think about random standard tableau, so what I mean is just take some distribution for partitions and then sample uniformly a random standard tableau. Then the existence of some kind of limiting surface. So you have some limiting shape for certain families around the partition, then you have some limiting surface for standard tableau, as proven by Bian in 1988. But this existence is completely implicit, so there is no formulas for the limiting surface. And then a lot of people get interested in finding the formula for these limiting surfaces. The same way we have a formula for the limiting shape of a Planchial distribution, right? We want to have the same for uniformly random standard tableau. This has been done for rectangular shape in 2004, and then for arbitrary shape, a lot of very different formulas were obtained by different mathematicians. So one of the goals of the talk today is to prove fluctuations for the limiting surface. So I'm going to explain what is the limiting surface, how we can construct a limiting surface, and how does the fluctuation around the limiting surface look like in a very general set. Okay, so the results I'm going to talk, not in all in full detail today, are the following. So first, we're going to identify necessary and sufficient conditions for low order numbers. So actually, first, I'm going to introduce a Laplace transform for partitions. So some kind of object which plays the role of the characteristic function you have in probability, but more adapted to partitions. And with this object, it's very nicely behaved, just as you want to have, just as you expect from a characteristic function. You have a necessary and sufficient condition for low order numbers, necessary and sufficient condition for a central limited term. And more interestingly, you have a way to characterize a multi-level central limit term, a multi-level low-order number. So multi-level here, I mean for increasing sequences of partitions. So not just for one random partition, but now you have a coupling between multiple partitions, and then you obtain some kind of limiting shape for that. And then you have applications with these results. So three applications of interest are we are able to describe the fluctuation for the Planchial growth process, which I'm going to define just in the next slide, which is a generalization of the Planchial distribution. Then you have a fluctuation for a generalized group process. So this means some kind of deformation of the branch-level group process, but I'm not going to talk about this result today. And then you have Gauss fluctuation for random standard union tableau of fixed shape, which we're going to do just at the end. So what we're going to do now is as follows. So first, we're going to present the result corresponding to branch-level group process with all definitions so that everyone can understand. Then we're going to describe how does a central limit term looks like and a multi-level central limit term looks like. And finally, just as a final example, we're going to describe the last result. Any questions up to now? So first, what is the Planck-Level group process? So the Planck-Level group process is simply a markup process on partitions. It starts from the empty partition. So you can look at the graph you have here at the bottom left. And then we're adding a box at each step with a certain probability, transition probability, which is given by the formula you have here. So at each stage, we have a partition, so we can only add boxes on corners. And then we have some transition probability, which is not particularly relevant right now. What is relevant is that if you take the induced distribution at a fixed time of this Markov chain, then you obtain precisely the Planck-Shell distribution. So this means that you can start from the partition, you run the Planck-Shell group process, now you have a standard Young tableau. You have this collection of increased partition, which we just said before is the same as standard Young tableau. Now we want to associate some high surface to it so that we have some kind of graphical representation for this object. So what we are going to do is introduce a high function. So with a high function h xt, which is going to be
the n of the time for the Markov
yes.
chain is the corresponds to the set
to the type we have, so the number of boxes we have.
the of course.
Yeah, the size of the partition.
This is the
yeah. So what we can do is fix some time or some step if you want. So for example, suppose that at step 13, the partition we're at is 5, 3, 2, 2, 1. And then we want to associate the height of x at this partition 13 to be the number of boxes you have at a certain diagonal. So for example, the height of 1 at time 13 is simply the number of boxes you have at this partition, have 3 boxes. So the height is going to be 2. Right. So if we do this for each time, have these functions which are these slices of a surface, and then if we put together all these slices for different time, you obtain some surface. So if you do this for example, the Planck-Shell group process, then you obtain a random surface which looks more or less like this. So as I was explaining before, you have some limiting shape for this random surface as n goes to infinity, and then we'll how does the fluctuations look like around this limiting shape. So well, here you have some representation how the limiting shape looks like. And then we study the fluctuation, and the fluctuation look more or less like this. And we like to have some kind of characterization of this fluctuation. So it happens that in this second, the fluctuation will converge to some conditional Gaussian Free Field. So what I'm going to do next is explain in more detail what this result exactly is, so in more precise mathematical terms. So first, what is a Gaussian Free Field? What does it mean to have a conditional Gaussian Free Field? In which sense this convergence is happening? But before doing that, already just from this you can see something interesting. The fact that here you don't have any extra terms for n. Right? So this means that these fluctuations are extremely small as n goes to infinity, which is a characteristic of this kind of models, which I particularly think is very interesting. Okay.
X is near the diagonal, or
X is going to be the space direction and the time.
yeah, but when you
yeah.
Okay.
Okay.
For fixed x and t, you don't have anything unique from x. You do?
Well, what did you mean?
This limit is for a fixed x and t.
So it's jointly for x and t. So we have convergence to a Gaussian process.
Okay.
So the Gaussian Free Field is exactly a generalized Gaussian that we're going to define just right now. So this is kind of the formal definition, but if you just want to have some informal definition in mind, the Gaussian Free Field is in some sense a very good model of what a random surface will look like. It will have some boundary conditions. So probably you're already familiar with what a Brownian bridge is, or what a Brownian motion is. So Gaussian Free Field is simply the generalization you will get if you go up to one dimension. You have two dimensions, then you obtain a Gaussian Free Field. So it is a two-dimensional analog of the Brown bridge, but one feature of this object, which is very nice, is that this is not longer a surface. So it means that you cannot really evaluate on a point a Gaussian Free Field, but what you can do is test it against a family of functions. So in this sense, it is a generalized Gaussian Free Field.
Yeah.
So this means that actually what you do is that you have some family of functions on where the Gaussian Free Field lives, or in this example in a square, but in the example where interest is going to be on the upper half plane, and then you can compute the integral over these functions over this Gaussian Free Field, and you obtain some random normal variables. Okay, so this gives you some idea of what a Gaussian Free Field is. But then there is some questions. So first, you may notice that here we are adding the word condition, and we're still not explaining which sense is where this is happening. And also, the definition I just gave in the following slide is for the upper half plane. But here the fluctuation seems to be happening only in some section, right? Only inside a parabola. So we need to fix these two things. Maybe.
Yeah. You just need to move them.
Until I
You don't click on it.
okay. Okay, so first we're going to identify the interior of the parabola with the upper half plane. So there is some explicit map to do this. Which is the map given here. So it means that if you look at the fluctuations, there is a way to move from each point here to the upper half. And notice that with this map, horizontal lines on the parabola will translate into semicircles on the upper half plane. So this is interesting because now let's think about how can we have some condition. And the condition is in fact already hidden in the height function. So as Joaquin was saying just before, the height function satisfies that it just count the number of boxes we have a fixed diagonal line. So if we just integrate over the space further, we're just counting the number of boxes we have a fixed time t. So this means that if we go back to the fluctuations, then if I integrate over the fluctuations for some horizontal line, I'll get 0, right? So the condition in here is simply that if you add all the infinitesimal fluctuations over horizontal lines, well, they add up to 0. And that's the condition we have on each line. And on the upper half plane, this translates into a conditioning over semicircles. Okay?
But this function where you're mapping is a conformal, no?
It's not conformal.
Oh.
Yeah. No.
So it's like you don't get a Gaussian free field on the parabola, you just get
No.
a Gaussian free field.
Exactly. Yeah. Yeah. Which is a problem because for other models, the fluctuations don't happen inside a parabola, but happen over more exotic kind of surfaces. And then we still need to map this to the upper plane to observe this condition.
And just so this condition GFF, I had seen it. So sorry. So your GFF, which type of boundary condition has 0 or free?
Yeah, 0.
Because the only case I had seen this 0 mean was when working with the free boundary GFF on the works of Mead, Sheffield, and company, where they, to build all of these surfaces, they actually do work with this mean 0. Do you know if there's something?
No, I didn't know about this one, so I will ask you about it. Yeah, I simply say that we have an explicit covariance formula. So you have this term, which is the one we had for the Gaussian Free Field, and you have some correction which correspond to the condition. Okay, so in which sense the convergence is happening? It's happening in the sense of moments. And so this means that if I integrate over polynomials over the space coordinate, then these random variables will converge to the random variables corresponding to integrated against the conditions of the and then we can restate the result. You just we have some extra convergence in the sense of moments. So at this point, I usually just stop for a second just to ask if there is any questions, because now we're going to move to the other kind of results, which are way more abstract. And
so in this sense, do you have also convergence in certain Sobolev spaces?
So I haven't extended to that point. So another question, for example, is what is the maximum kind of functions for which you can have this convergence? And I don't have an answer for that. So I'm pretty sure you can probably extend this a bit, but I don't know to which one. So yeah, I would say that for this work in particular, the main goal was simply to obtain a Gaussian some familiar.
Gabriel, I forget the little bit. Some things like this were known before, like some aspect of this. I'm trying to
for partition, no.
Nothing.
The other height function I knew it's like the one of dimers. So is there a relationship between dimers and this Young diagram, or there is?
Yes, so there is certain dimers for which we believe that if we take some kind of limited information and some probability distributions, then we should see something like this. But it's very unclear because we expect to see a Gaussian field if we do the formations of dimer models. And to obtain this kind of result, there is a need to do some additional procedure, which is not really feasible to do if we start from dimers. No. Okay, so next I'm going to excuse myself. I need some definitions from algebra. So a brief review of representation theory of this metric group. So our representation is a group homomorphism starting from a group to a group of unitary matrices. And a character is simply taking the trace of the group homomorphism. So we are taking the trace of a matrix that depends on some group element. Now, irreducible representation of the symmetric group are indexed by partitions. And the dimension of an irreducible representation is precisely the dimension lambda, so the number of standard tableau shape lambda. And this is the reason why we're using this notation to denote the number of standard, because it comes from representation theory. It's actually the dimension of a vector space. So we're going to denote the characters for irreducible representation by chi lambda. And the characters are invariant on the conjugation, so there is a trace here. So they are going to be invariant on the conjugation. And for this reason, we can notice that, well, if we take some permutation, if you take the conjugacy classes of a permutation, it's precisely partitions. So in some sense, characters, while we're applying them to elements to the symmetric groups, permutations, in some sense, they are actually a better tool to study partitions. And finally, notice that if you evaluate some irreducible character on identity element, then we're taking the trace of the identity matrix to obtain precisely the dimension of the irreducible vector space, which is dimensional. Okay, so keeping this in mind, now we can introduce the definition of what is going to be the Young generative function, or this kind of Laplace transform for partition. So I want to define. So we want to define some kind of multivariate Laplace transform, only that instead of random variables, we're going to have certain permutations. So what it means is that I want my random variables to be cycles. So for example, you start from the cycle, then you have a cycle of length 2, then a cycle of length 3, etc. So we want to define some kind or construct some kind of Laplace transform so that these are random variables. And immediately we'll run into a set of problems if you try to do this. So the first problem is that if we want these things to be bona fide random variables, well, in some sense, if I take powers of it, I want to recover the combinatorial data of the distribution, right? But if I take powers of these things, then we're losing information pretty fast, right? So if I take the square, for example, 1, 2, then I take the identity element, and then I always run between these two. Right? So rather than taking powers of these, we're going to take a disjoint product of these. So for example, of course, the square of the identity is still the identity, right? But then rather than taking the square of it, I want to take some kind of disjoint product. So 1, 2, 3, 4. And then again 1, 2, 3, 4, 5, 6, etc. So we need to do that for each one of the cycles. But then also, if I take products between the cycles, then I may also run into some combinatorial problem, right? We're going to force all this family of things to be disjoint. So once you have this small correction, then you can just take your usual definition of an exponential function, so a Taylor series, and replace the force of your random variable with this kind of disjoint powers. So if you do that, then you obtain the following formal element we have here after adding some rescaling.
So I really didn't understand why when you were like squaring the 1, 2, why do you get the 3, 4 and not like the 5, 6, for example? Or like the 4, 5?
Oh, it's because I want to have some kind of disjoint product of cycles. So if I take the third power of it, I don't want to obtain the density element. I want to obtain a product between 3 transpositions, so 3 cycles of my thing.
And how do you choose which transposition you are putting in each?
So there is of course an infinite number of ways to do that.
Yes.
But the reason why we will not care about this is because after you have all this notion, then you still want to have some notion of expectation. And the notion of expectation is going to be played by a character. So if when I evaluate a character over any of these objects, they are invariant to a permutation, so actually it doesn't matter which one you choose.
Okay, so what they have to think is that they have if you have 1 transposition, the product of it is 2 transpositions.
Exactly.
Okay.
Exactly. Yeah. So you do this for each. So this is just some formal notation to say just what I said before. And then you add some rescaling term. Then you have some factorials just so that you have exponential functions, they form a product of it, and then you have some element that lives in some weird algebra. And finally, for each probability measure over any partition, you can associate some character, which is simply a linear combination of the irreducible characters normalized. And you can think that this plays the role of an expectation because when you evaluate this character over the identity element, so expectation of 1, then you get 1, precisely because the character over the identity element is going to be the dimension, and then you get a sum over the probability measure, which gives 1. So all of these can be formalized using, or more or less formalized using free probability. So what I meant to say is that you can think of this thing as some kind of extension of some notion from free probability, and you can formalize it using some algebra. So the resulting thing. Yes.
And why the normalizing term, or what is?
So I'm pretty sure you don't actually need the normalizing term, but this is the normalizing term we are going to use for the famous distributions we studied. So for
Does it have physical meaning, or is it just convenient?
so it's convenient to have it in the definition, but I believe that probably you can study other kind of.
It's not a combinatorial fact.
No. So the resulting object is just this abstract object, and we're going to call it a young generative function, which the reason is historical because there is already a short generative function and there is other kind of generative function of this sort. But if you want to think of this in a simple way, just think that this is some kind of Laplace transform for partitions. And after looking at all the previous definition, you may be freaked out and believe that how do I actually work with this very abstract object? But actually, you can work.
Sorry, just so I'm a little bit lost. So the x1, x2 are partitions.
No, these are just free variables. So you know for the characteristic function, right? You will have something like some exponential of some lambda, and here you have your random variables. So these lambdas. So for a multivariate generative function, right, you will add some sum here. Multivariate Laplace transform. So you have something like this. So these things are exactly the. So it's just
but in that case they live in the complex plane. This xi was
yeah, you can think of this as living in the complex plane. Yeah.
And what they we still haven't seen where they are multiplying. No.
So in full generality, we just need them to be formal variables because we can work with this in a completely combinatorial way. So okay, let's see an actual example of this. So if you start from the Planck distribution, so reminder the Planck distribution is given by the formula here, and it is a well-known fact that if you compute this kind of associative character we had in the previous line, so this thing here for the Planck distribution, then the character you get is very nice. It's simply equal to 1 when you evaluate an identity, and it's equal to 0 over any other permutation. Okay, so then you can compute the same, and what you get is simply an exponential function only over the first variable x1. Okay, so we're going to keep this definition in mind, and now I'm going to introduce another definition, and with these two other definitions, we can state a my result, which is
sorry, I'm still better. So the x2 here, what is the, because you're computing u infinity, but I still haven't managed to keep it in my head. So u infinity has the term x2. Can I
yeah,
that for infinity? So I have
Yeah, you have a xk for each k. So xk correspond to the k here correspond to the length of the cycles.
Oh, I see. So this is the term speaking about the length of the cycle, and just when the cycle has length more than one. Okay, I see. Now I understand.
So this is just a formal. So anyway, so
Yeah, but you only get x1 because of your choice of products.
yeah.
It's only the identity which you only see the first.
Yeah, exactly. Yeah.
So we should get some, it feels like you will, with this you could get some kind of central limit theorem in this weird free.
Exactly.
Because somehow it is the simplest one you could get now.
Yeah. But we can do the computations in other models, of course. Only that it becomes more and more.
But with this help you, so is there something like, is this generating function, is there something like the sum of two things will behave nicely as it is with the sum?
Yeah, so I don't think it's going to be the sum. It's probably going to be something like external sum of representation theory, like something.
Yes, and this should converge. So in a way, the Plancherel distribution would be like a certain, play the role of the normal random variable.
Yes. Beautiful. Okay, so now actually we will not work with partitions using the Russian notation. Actually, we'll need to do some kind of change of variables. So how am I doing in time? Like, is it
You still have like 25 minutes,
okay? I think we should.
including questions, but
Okay.
we have been after that.
Okay, cool. So there is a way to translate between diagrams or continuous diagrams. If you just take the completion of the space, you get a space of functions which call continuous diagrams. And there is a homomorphism between the space of continuous diagrams and probability measures over the space where the diagram is not equal to the absolute value. So the way to translate between these diagrams and probability measures is very implicit. Is via the Stieltjes transform. So if you take the Stieltjes transform of this probability measure and you take some kind of Stieltjes transform of the function you're getting in Russian notation from the diagram, then there is some relation between this, and this relation is not linear. So you have some exponential function. So there is some kind of implicit formulas, but they are not important here. What is important is that even if this formula is not nice, it is nice enough in the case of actual diagrams. So we're not taking the limiting functions. So as an example, as two examples. So if you take a Young diagram, then we can actually compute this scalar transition measure. So simply compute all the minima, local minima, local maxima. And then the probability measure you're going to get is going to be supported over the local minima. And then there is some explicit coefficients you can compute doing some formula that relates the minima and the maxima. So for example, here you have how does this Markov train measure will look like for the example of this particular partition. So this is one example. So you can do explicit computations for diagrams, which is nice. And secondly, if you think of the Verschicke-Logan shape curve, so also when you compute the Markov train, the transition measure corresponding to that shape, you obtain the semicircle distribution. So the semicircle distribution, if you have any kind of free probability, something like that, it's kind of, in some sense, the normal distribution for some different way of thinking about independence, which is called freeness. Okay, so now with these notions in mind, we can state our main result. Sorry, with two extra definitions before. So, so we're going to say that a family of probability distributions, so any family of probability distributions over partitions is central limit theorem appropriate if it satisfies the following three properties. So if you take the partial derivatives of logarithms of this kind of Laplace transform, then you obtain some limit, and we take note of these coefficients. If you take two partial derivatives and take some rescaling, then you also obtain some limit, which is going to depend on the partial derivatives you take. But if you take three or more after some rescaling, you get zero. So this is one definition. And the second definition, if we look at the normalized moments of the Markov train transform of a random variable, okay? And then this random variable satisfies a central limit theorem. So it means that after rescaling, these things will converge to a Gaussian process with some given expectation and some given covariance. And now, as we hope, because we want this object A to play the role of a Laplace transform, what happens is that these two definitions are equivalent. So,
What question do you need them? Ah, okay, so they are Gaussian properties.
Yeah. so they are equivalent, and also we have a way to translate between these two. So the first statement of this term is that central limit term appropriate and satisfying a central limit term for some family of distributions is equivalent. But also, if we construct two formal series, taking the coefficients i's and coefficients dij we had before, then we have a way to compute the limiting expectations and limiting covariance up from these formal series. So if you have this ugly formula, don't lose time and energy reading this formula. If you want, of course, you can do it. But what's important is that there is a formula. And because there is a formula, we can analyze this formula and try to understand what is the actual covariance and forward the Gaussian field. Right? So let's run an example. And in this example, we actually reprove this very Raposo term that we presented at the beginning. So if we start from the young derivative function for the Planck transform, which is use an exponential, then you take logarithm, and you can use x1, and you can compute partial derivatives and verify that it is central limit term. So it satisfies central limit term because of the result. And then you have an explicit formula for the limiting expectation and explicit formula for the limiting covariance. So if you do a quick computation here, and these brackets here means that we are extracting the coefficient corresponding to the term z to the power minus 1 and zw to the power minus 1 in the formal Fourier series. So if you do this computation here, you can Catalan numbers which correspond to the moments of the semicircular distribution. And via the series transform, you recover the result we have the beginning of the vertical potential. Okay, so this is just for single level. Now, what about multi-level? So for multi-level, we need to first explain how do we sample and the standard unit tableau.
Can I
Yes.
I'll forget later, so I'll ask you now. Is it from here that you see this sort of mapping of the parabola to the half plane in the...
So I don't have any good explanation of why you have that particular mode. So as far as I know, after asking a lot of people, it's used from experience. So someone found it, and then it happens.
It's just lucky that that thing goes to...
Yeah, and actually we have math for other kind of shapes, and they are very implicit. So how can we sample a partition? So I'm just going to present one way at the time. So you have your distribution row n for partition of size n, sample a Young diagram, and then you can sample uniformly a random standard unit tableau of that shape. And then you have, of course, automatically a collection of partitions, and then you have a probability distribution used for each one. So that's how we can sample as a random standard unit tableau. And then the result we have is that if my original distribution is central limit term appropriate, then automatically we have convergence in the sense of we have convergence to a Gaussian process for all the different levels of the partition. So this parameter, so this is exactly the same as what we had before, only that this parameter alpha corresponds to the level of the partition. So we can take the n/2 partition, for example, over all the whole partition of size n. Right. And again, we have an explicit formula for the expectation and explicit formula for the covariance, which we can analyze thanks to result. Okay, so do you have any question at this point? Any additional question? Okay. So let's see another example. So
yeah, I do have. Forget about it. So to grow this, you always use the same Markov process to grow the...
yes. So we're always
defining the same way for general row.
Yes, exactly. So if you are lost at this point with all these kind of statements, then we can wake up now, because the next example is nicer. So another example of distribution we can have besides the Planck process is the following. So you can choose some limiting shape, for example, a square, and then sample a standard unit tableau of that shape. So for example, you can start from a square, you have just one box, but then you can subdivide this limiting shape in more squares. Right? So you can then have a 2x2 box, a 4x4 box, etc. And from each one of these, you can sample a standard unit tableau uniformly at random. and then take the limit as n goes to infinity, and ask yourself, do you have some limiting surface? What are the fluctuations on this surface? So we already know there is a limiting surface because the existence was proved by Gelfand in all cases, essentially. So we have a random surface in this case, and you have some limiting surface, and then we ask, okay, what are the fluctuations around this limiting surface? And something nice is that we can apply the result I presented just before. Because if you just look at the limiting shape, of course, that's deterministic. So just the largest partition automatically will satisfy a central limit term. And because our result is an if and only if, we know it is central limit term appropriate. So we can apply the central limit term to all these levels. So we know then that the fluctuations around each one of the partitions is going to convert to a conditional Gaussian Free Field again. So something nice, which is a surprising feature of this model, is that we have a different condition. And the reason we have a different condition is because here the fluctuations are happening inside the circle, right? But now the map we have from the interior of this disk to the upper half plane is going to be different. So before, the condition of the upper half plane is that if we integrate over semicircles, we add up to 0. Now we still have something similar, only that it's not going to be semicircles, it's going to be something different. And this is going to change for each one of the models we have. Yeah, so how much? I still have 15. Okay, that's very nice. Okay, then we can do the whole presentation. Okay, so how can we prove this kind of results? So in 5 steps, we first want to relate the characters to the transition measure. So our main result relates this kind of young generating function with this character transition measure. So we need a way to do this relation. And very nicely, this was already done by Gelfand. So Gelfand has giving some operator interpretation to some formula from Gelfand that was trying to prove some link using free probability between random partitions and character of the symmetric group. We have a way to relate these two objects. So the way to relate these two objects is that we have some operator, which I'm going to show in a few slides. But we need to study this operator in full detail to actually run the whole computation. So first, we need to expand this operator and have explicit formulas for this operator. And for that, we need to work on the Gelfand Tsetlin algebra of the symmetric group. And secondly, once we have formula for this operator, we actually need to manipulate this operator and manipulate the formulas to identify the contributing terms of the expectation, contributing terms of the covariance, and contributing terms of higher equivalence, which is how we are identifying the Gaussian process. So these 3 steps correspond to the general result corresponding to the if and only if. But then if we want to study applications, for example, to taking random standard unit tableau on the square, then we need a way to identify the Gaussian field, which in this case is not as clear as in the Planck-Gelfand process, because for the Planck-Gelfand process, we have this nice map between the interior of the parabola to the upper half plane. But now we'll have some kind of different fluctuation regions, right? So we still need a way to map these fluctuation regions to the upper half plane. So for that, we need to do 2 things. First, we need to translate between character transition measure to height function. So we know that a relation is given by the Markov-Crane transform via character transition measure, right? And if you remember, this is a relation between 2 still just transformed via some exponential. And this relation is not linear. So because it's not linear, it's not necessarily clear why Gaussianity on one side will mean Gaussianity on the other side. But this is something we managed to do via some combinatorics. And secondly, we need to translate between the liquid region, so the fluctuation region, to the upper half. And for that, we take some maps that were taken from Dus and Metcalfe, and we do some kind of deformation of these maps to translate in a very implicit way between this liquid region and the upper half. So just to have some flavor of what this means, I'm going to present the operator. I'm going to show how we can compute just the first frame of the operator. And I'm going to explain what the general problem that we solved in part 2 and 3 looks like. So the operator is the following. So the operator is just a matrix, only that rather than having real values or complex values inside, you have elements of the symmetric group. So if you take powers of this matrix and then take the trace of this matrix, this gives you some element that lives in the algebra of the symmetric group, some linear combination of elements in the symmetric group of permutations. And we can use this element to act on characters simply by multiplying what's inside. And when we do that, and we evaluate the character and the identity, then we're going to recover exactly the joint moments of the Markov of different powers of the Markov transform of random partitions under your fixed distribution. So this result allows, in some sense, to translate between the Haney function, between the young generation function, which is going to, in some sense, put together all these characters, and the Markov the curve transition measure, which is what we're going to have at the left. Okay, so as I was saying before, we need to understand how does the trace of powers of these things looks like in a very general way. So let's just look at the first term. So the first term means this is going to be some linear combination of permutations. So what is the coefficient, for example, that is next to the identity permutation? So the way we can do that is as follows. So if we take trace of powers of the matrix, we get product of transpositions that looks like this. And if we want to know what is the coefficient that gives you the identity element, we want to count the number of ways this product will give you the identity element. So in this particular case, this problem we can simply solve using the pigeonhole principle. So you can put all the partitions, for example, in a circle, and you can quickly notice that if you want the leading term of this product, you need the leading term is going to be given by the number of ways you can form non-crossing two partitions of this kind of plan. And if you remember combinatorics, this is given by the Catalan number, and the Catalan numbers is what is giving you the semicircle distribution. So which is what we were expecting. Now this is just for the first coefficient, right? It corresponds to the identity element. But then we want to do that for general permutations, and then we want to take products of this operator, and we need to understand how they interact. So the kind of more general problem we need to solve is the following. So take some conjugacy classes given by partitions, lambda 1 up to lambda r, and then sample some permutation uniformly at random, and each one with conjugacy class given by that partition. And then take the product of all these permutations. This is going to give you some new permutation, right? And then we want to know how does the leading term of this permutation looks like. And then we need to know how does the corrections of this leading term looks like. So this is, in some sense, the most general combinatorial problem we solve in step 2 of our general proof. So finally, I'm going to just quickly show some other results we have from this work. So we obtain new combinatorial formulas for cumulants. So besides Plancher, another example of importance are Schur and Gelfand distributions. A different question that we can ask for is, what if you sample some standard in Tableau, and rather than looking, for example, you have your partition, and rather than looking at some level alpha, which is going to be some coefficient a n, for example, or a within between 0 and 1, right? We can ask, what if alpha is something that decreases linearly, for example, square root of 5. And then we have that this partition, of course, is collapsing near the origin, and then we can ask what is the limiting shape, how does the fluctuation look like? And we're able to answer that question. And we obtain exactly the limiting shape we have for Plancher distribution, which in some sense further justifies universality. And finally, a different kind of question that we are answering for this work is we are able to describe the fluctuation for the distribution of the location of the n box in a random standard Tableau. So if you pick your random standard Tableau, then you can pick some box k, right? Of course, it's in a random position. And then we can associate some probability distribution to this position, and then we can ask what is the fluctuation of this probability distribution. We can answer that question, which is a conjecture posed by Peter and Romick in 2004. And thank you so much.
Gabriel, for the very nice talk. Questions? Yeah, any additional questions? The ones we have been asking.
To compare with, so here you have like a specific measure on your partitions, but it should work for class, no?
Yeah. So the if and only if result is
Okay.
For-
So do you have another? So do you have another example for which, like a specific law for which it also works? Or
So there is three kind of examples that are the main kind of examples we study. So the first one is Planck-Gaussian process, famous one. Then we have some deformations of the Planck-Gaussian process which come from representation theorem. So there is a whole different interpretation of the result of interest from algebra, and there is some probability distribution induced by the infinite symmetric group, which we can interpret as some kind of Planck-Gaussian process, but with extra rate of boxes coming from the sides. And the last example, which is the one for fixed shape, which comes mostly because there is a whole community of people that were interested in finding explicit formulas for limiting shapes of some fixed partition. So you fix a partition and then you sample a standard Tableau, you have some limiting surface, and they were interested in finding the formulas for this limiting surface. So now we describe the fluctuations for this.
and there was something. So at the point you get explicit formulas for the Gaussian, so the Gaussian fluctuations.
Yeah.
But the fact that it becomes a GFF, it is just because of the law you are taking, or it. So this is where I am lost because there were some computations there.
Yeah.
So the universality of the GFF will come.
Yeah. So the GFF is for these three examples. So the three main examples, and also for other computations that we have done. For example, Schurwell more or less can be interpreted as some deformation of something coming from the infinite symmetric group, and Gelfand is something that is just different. But we do the computation and we also obtain GFF.
So there could be something like the approximation you do for the CLT that also works here, that allows you to additionally add to your theorem that actually you are going to a GFF condition. Or there is.
Yeah, I'm not sure if I understand that
So
question.
it's like somehow like you are always getting a condition GFF, but every time it's because you are doing explicit computations. It's like I'm doing a CLT first with a Bernoulli because I use an approximation, and then and I'm doing it with other things. But so there could be something missing, which show you why you are always getting a GFF. Or this is like there are hope to say that there is a whole class that is converging to a GFF, not just to a Gaussian thing.
Oh yeah, I see what you mean. Yeah, I mean, in principle, we could ask about what is the kind of maximal class of distributions that satisfy this. I think we could maybe reverse engineering the results here to do something like that. Yeah, I think so. But for example,
it's the same GFF, right?
Sorry?
It's not always the same condition on the GFF.
Yeah, it's not always the same condition.
It's always like a projection of a GFF. So it's just like when instead of conditioning, one can think about as projecting. It's the same for Gaussian. And somehow projection seems more likely enough.
Okay. Yeah, so when you mentioned some connection with probability.
Yeah.
But so tell us, is there any context or general ideas from that context that suggests that there is some Gaussian fluctuation of this object? I mean, some other context. Because Gaussian is not so natural in the context of free probability. I mean, it doesn't appear so. I mean,
yeah, so I think that in a certain kind of coordinate setting. So I mean that, for example, if you think about partitions in terms of the period of transition measure, then you observe the semicircle distribution.
Yeah.
So it seems that in certain coordinate setting are better in some sense to relate with things with free probability. Now, why that's happening, it's totally different. So,
but in a way, I mean, since you have the semicircle law, I don't know, think of fluctuations that are rather like random matrix type.
Yeah, so random matrix is a good example. For example, why this model is kind of weird, because in random matrices, when you study the empirical distribution, right, you observe the semicircle distribution, and then when you can associate directly to the empirical distribution a height function and observe the Gaussian free field. So you can observe the Gaussian free field and the semicircle lives in the same kind of coordinate setting. But in this here it's different. Here you have the symmetrical law, but then you need to do a kind of change of coordinates to the high function to observe the Gaussian field. I'm pretty sure it's not Gaussian field. Actually, don't do the computation, it's not Gaussian field on that side. So why you have this difference, I don't know. That's I'm not sure if it's completely a mathematical question.
The other questions? I think I have two, but let's see. So, maybe I missed something, but the brief sketch was the sufficient. Like, how do you get that the only if? How do you know that CLT implies CLT appropriate?
Yeah, so in some sense we reverse engineering the whole proof. So if you have that is satisfied central in term, then we can translate that into some combinatorial information. So we need to have some higher cumulants converting to zero. We have some form of equivalence for the expectation, right? And then we need to identify how these terms tells you how does, for example, the young geometric function after taking certain derivatives and after certain rescaling convert to zero. Right? So that's what we're at.
Okay, I have time for the last one. Maybe this is naive, but do you think this extends to skew partitions? If I say fix just out of curiosity, I don't even know if the height is there a surface known in that case. Or?
Yeah, I'm pretty sure there is no literature on it, but yeah, it probably convert to some relative of the Gaussian field. That's what I would expect, but I don't think it's going to be exactly the same of it.
Maybe just the domain changes.
Yeah,
No idea.
yeah, I don't.
Okay, anything else? Otherwise, Damian.
Yeah, there's this paper about like CLT for short generating functions.
Yeah,
From Goring Buffalo. It's like similar flavor or?
yeah, it's a similar flavor. Okay. Kind of in kind of representation theory terms. What they do is work for the unitary group, and here we work with the symmetric group. So I think for me the crucial difference is that in the unitary group, the kind of operators you work on always are you always take derivatives. So you only work with partial derivatives. So the combinatorics becomes much more transparent. So a lot of things commute. But here, because we are working with the symmetric group, a lot of things will not find a way to push forward these conditions.
So I guess that setting doesn't have like the free probability flavor.
I think there is some people working on it. I think I have to say Buffalo, who is one of the projects that has some papers on that. I'm not sure how deep they go through it.
Anything else? Otherwise, let's thank Gabriel again. That was session. And yeah, I mean, I know we have more Jimmy now, and
We have more what?
I mean, if you are the
Yes. So we are going to go somewhere. I would say let's meet at 5:30 downstairs.
5:30
Or 5:30? Is it 12?
5:20.
Okay, 5:45. 5.
Bueno, no español.
Ya, un cuarto para las 6. Un cuarto para las 6 abajo.
Pero bueno, ya, y en un momento más decidimos si vamos a donde siempre o no.
Sí. Y en un momento más Pablo va a escapar y traer más.
¿Los jugos?
Los jugos.
Que se me quedan ellos.
Mañana me toca ir a...
Las condiciones sean súper parecidas a lo que tienen ellos.
Vale la pena ir.
Claro, la idea que tienen ellos es que la short generating function juega el mismo rango. De lo que quería yo era considerar lo que también fue lo pero las condiciones así como la derivada parcial también afectan las características. También está el tiempo de los tiempos.
Que no se siente muy bien. Particiones que cumplan alguna condición que te interesa. Por ejemplo, no sé, que dos sean números primos. Sí, claro que se puede hacer.
Podrías tener funciones.
Podemos poner como ese proceso como marcoviano de particiones siempre que cumpla alguna condición prescriptiva.
O sea, en principio siempre vas a tener distribuciones de probabilidad para las condiciones que tú quieras.
Pero eso es un objeto, pero ¿van a tener relevancia o pues?
Esa pregunta.
Ya. No gastaba que se podía estudiar así.
Por ejemplo, lo que pasa es que vas a tener comportamientos muy diferentes como la distribución. Por ejemplo, para la distribución uniforme uno no observa el Gaussian Free Field, sino que observa una superficie plana. También es gaussiano, pero es completamente diferente. Entonces, me preguntas por cómo saber el cuándo. Yo que parto de una, pero empujo y hay gente que lo hace. Para los últimos 20 años, mucha gente se ha puesto a estudiar particiones.
Hay que cortarlo, ¿no?
Muy importante.
Y el verde se corta.